question that people had voted on. A5. Propane gas is one of the nation's most versatile sources of energy. Right. And I think it's, I think when I originally wrote this problem, it was only 4%. I think it's higher now. I think natural gas is probably at like 15% just because of fracking and all that. So I should probably update that question to properly associate it, in those cases. But yeah, so I mean it's used a lot and stuff. So part one, right? What is the delta HF? Right, the delta HF formation for propane. Right, so you can just simply look at the table, and so in this case right here, right, the delta H of formation for propane, right, C3H8 is equal to negative 104 kilojoules per mole. Right, and so knowing what we know about standard enthalpy of formation, right, the reaction to form them, right, is you always start off from the elements. In those cases, right, the standard, whatever the elements are that constitute it when they're at, standard conditions. In these cases, right, so 1 atmosphere pressure and 298.15 Kelvin. And so for that, right, to form C3H8, right, you have, graphite plus H2 gas, right, and that's going to form propane gas, right? And so if we balance all of that out, right, so there should be 3 equivalents of carbon and then 4 equivalents of H2 gas, right? So that's the balanced equation for the formation from the elements of propane gas. Now, right, if we look at the delta, the next question is, right, is this reaction endothermic or exothermic? Why? So the thing to look at, right, is that you're the delta H formation, you can see that it's negative. So if it's negative, that means that it's exothermic, right? It's releasing energy in that case. And so the thing is, right, the reason that it's exothermic is because you're going to be forming a lot more bonds in those cases, right? So graphite on its own, right, doesn't really have, I mean, if you understand in solid state chemistry, right, I mean, graphite does have bonds, right? But in terms of how we look at it and think about it, right, it doesn't. And in the case of H2, right, each hydrogen is just simply bound to one other hydrogen, and they're both, together. And so there's essentially just like one bond there. So we're really only looking at 4 bonds on the reactant side. But if we're looking at the number of bonds that we have on the product side, right, that shoots up, right? There's 2 carbon-carbon bonds, and we have 8 carbon-hydrogen bonds, right? So there's a lot more bonds that form, and so there's a lot more energy, right, that gets released because now we're forming something that's more stable in this scenario, right? So there's more energy that's being essentially, released in those cases and being, transferred outwards. And stuff, right? So because you're forming more bonds, right? It's a pretty decent explanation as to why that's exothermic. It isn't always going to be the case, right? Because you also have to think about whether some bonds are stronger than others, right? And that's where like thinking about bond energies kind of comes into play. But just when you're going from the elements, most of the time, right, you're going to probably have an exothermic process. I mean, there's some, right, delta HFs, right? And I think we had seen that if you were looking earlier, right, and watching when we were talking about, I think B2, right, the delta H of formation for right, forming just simply H dot and O dot dot, right, the 2 radicals, right, in those cases, right, those were positive, and that's because you're breaking the bonds, right? They're just simply becoming atoms, monoatomic atoms that are just hanging out on their own. You're not really forming anything new. Those are the things to consider. Part D, how many moles of H2 are needed to produce 1090 kilojoules worth of propane according to the balanced thermochemical equation? So now, right, what we need to think about in these cases is the relationships of everything, right? So, excuse me. So if we're forming, if we're going to be putting in 1090 kilojoules of energy, right, we can calculate using the delta H of formation how many moles of propane we're going to be able to form, right? So if we do that, right, we know right here that what we have is, right, the delta H of formation, right, the delta H in this case is going to be negative 1090 kilojoules. And so that's going to then be equal to the number of moles of propane, C3H8, times the delta H of formation for propane, so C3H8, right? And so what we're trying to go for, right, is what this number is, so we can rearrange all of this. So what we have now is NC3H8 is equal to delta H over delta H of formation of C3H8. So we plug in our numbers. We have negative 1090 kilojoules over delta H formation is negative 104 kilojoules per mole, right? So kilojoules cancel, moles goes on top. What we get is negative 1090 divided by negative 104 comes out to 10.48 moles of propane, right? C3H8. Right, so that's how many. So when you put in, right, to whatever your vessel is or system, right, when you put in, 1090 kilojoules of energy to, your graphite and H2, you should be forming then 10.48 moles of that. So all we need to do now, right, is just simply think about, well, what's the ratio between the two of them? And so for every mole of C3H8 that's produced, right, we're going to be forming 4 mole. We have to use 4 moles of H2. And so, all we have to do now is just simply take this and multiply that, right, by 4, because the ratio, right, so let me just, the amount of H2, right, is going to simply be, right, for, right, so you have 10.48 moles of C3H8, right, and so then the ratio there is that for, every 4 moles of H2, right, you form 1 mole of C3H8, right? So those cancel. So you end up with 4 moles of H2. So you have 10.48 times 4, you get 41.92 moles of H2, which is what I have right here, right? So that's what the relationship is. So in terms of how to approach that problem, right, you first want to calculate how many moles of propane you're going to be producing, right, when you put in that much energy. And then once you know that, right, you just simply use your balanced equation and you can figure out then how many moles of H2 are required, right, based off of that ratio. So that's how you do D. Part E, how much heat is produced during the formation of 30.1 grams of propane. So very similar problem, right? So the first thing we want to do, because the delta H of formation is in moles, we want to convert our mass of propane into moles, right? So in this case, that's going to be N, right? In our scenario is going to simply be the mass over the molecular weight. That's the first thing we want to do. So that's going to be 30.1 grams over, what is it? So it's C3, so that's 12.01 times 3 plus 8 hydrogen, so that's 1.01 times 8. That comes out to 44.11 grams per mole. Right, grams cancel, mole ends up on top. What we get is 30.1 divided by 44.11, which is 0.682 moles of propane, right? So that's how many moles of propane we have. And so, right, if we consider all of this just simply to be occurring at constant pressure, right, we can just simply assume that Q is going to be equal to delta H, and delta H is just simply going to be equal to N times delta HF in this scenario. And so now we know the moles, right? So that's 0.682 moles times, right, delta HF is, or delta H of formation, sorry. I should stop saying delta HF. Negative 104 kilojoules per mole, right? Moles cancel. So what we get is 0.682 times negative 104, negative 70.93 kilojoules, right? Which I think is what I have. Yeah. I mean, so yeah, so right, so it's I should probably fix the sign. On the answer key because I put down 71 kilojoules there. It should be negative 71. That's a mistake again. Answer key. This is what, A3, which again is probably why people wanted me to go over this. Or it's A5, not A3. Excuse me. Right, but you generate 70.93 kilojoules in that formation. Next part, write a balanced chemical equation for the complete combustion of propane. What additional reactant is necessary for a combustion reaction, right? So combustion reactions are, excuse me, when you, burn stuff, right? And so if you've ever heard of the fire triangle and stuff, right, you need, fuel, which in this case is going to be propane. You need a spark, right, to start the fire or the combustion. And then you need, an accelerant, right, or whatever, and that's usually O2, right? Oxygen is the typical um, um, gas, right? That is part of a combustion reaction. So, right, what a combustion reaction is going to be C3H8 gas plus O2 gas, right? And then if it's a clean combustion, right, all you should do is form CO2 gas plus H2O gas, right? And so if you ever write, when people talk about like fireplaces and fires and stuff like that and having like carbon monoxide poisoning, so what's happening in those cases is that you just actually aren't having enough oxygen go through, whatever wood and stuff like that you're burning. And then so what ends up happening, right, is that it's not doing a clean combustion because there's not enough oxygen, so it ends up forming carbon monoxide, and that's dangerous. That's how you can suffocate and die. So always be careful and be safe. So yeah, right. So that's the general equation. So now we just got to balance it. So if we look at it, right, there's 3 carbons on the left. There's only 1 on the right. So if we take the CO2, multiply that by 3, right, we get that value right there. For the H, right, there's 8 on the left. There's only 2 on the right. So we multiply that by 4, right, we get 4 H2Os. And so now we just need to balance out the oxygens. And so we have 6 oxygens and 4 oxygens. So that's 10 oxygens in total on the right. On the left, right now, we only have 2 oxygens. And so if we multiply the O2 by 5, right, we're at 10 oxygens. And so that's our balanced equation in this case. Now, the next part of the question is calculate W, right? Calculate work for the reaction at a constant pressure of 1 atmosphere, right? So if we're assuming that what we're doing is constant pressure work, right? Work is going to be equal to negative P delta V in this case. And so, wait a second. Did I not put, why doesn't it say the rest of the question? It's so weird. Did I not include the rest of the question on the, I swear if it's versioning again. Let's see. I think I forgot to put that in the, I'm sorry, guys. It's supposed to say like at 1 atmosphere. I don't know why I had it in the key version, but not in the problem version. It's just, sorry. I'm frustrated with myself for not doing that correctly. Okay. Well, so technically, right, this is supposed to be happening at 273 Kelvin. But I realized I forgot to put that in the problem, which I apologize for. But yeah, so we're at 273, right? And so again, right, so work is negative P delta V. And what we can do, right, is that if we're looking at the equation, right, that we had gotten from part F, right, what we can see is, right, if we consider all the gases to be behaving ideally, is that we can see that in terms of reactants, right, we have 6 moles of gas, right? There's 1 mole of propane, 5 moles of O2. And then in terms of the products, right, there's 3 moles of CO2 gas and 4 moles of H2O gas that form. And so, right, if we add all of those up, right, what we have is 6 moles of reactant gas, 7 moles of product gas. So if we look at the delta N, right, delta N in this case of gas is going to be equal to, +1, right? Because it's, 7 minus 6. And so what we can do is, we can use our a slightly different equation, right, to do the work, right? Because if we use the ideal gas law, right, which is PV equals, nRT. If we know that pressure is constant at 1 atmosphere, if we know that temperature is constant at 273, right, we know that the number of moles of gas change, right? We have a delta N value here, right? That changes. That means then that the volume has to change, right? So we have P delta V over here. And so, again, right, this is this right here. So we can just simply plug in the delta nRT for the work part. So if we have work, right, that's going to be equal to negative delta nRT in this case. And so plugging in our numbers, right, we have negative, and then now, right, we have 1 mole, right, that forms. In terms of R, right, that's going to be 8.314. There's no times 10 to anything. 8.314 joules per mole degrees, or Kelvin, sorry. And then the temperature rate is 273 Kelvin in this case. And so what we get is -1 times 8.314 times 273. And so what we get is work of -2,270 joules, which is what I have right here, right? But you guys weren't able to do that math because I forgot to give you guys the temperature, which is my bad. Right, but that's how you do it. That's how you approach it, right? So if when you're looking at how much work a reaction does and stuff, if the pressure's staying the same and the temperature's staying the same, right, the volume that that system is occupying will change. Right, and so you can calculate then the work that happens in that case by just simply, plugging in for P delta V, right, delta nRT, in those cases, and so you can kind of see what goes on there for all of that. Right, and then finally, right, calculate delta H of the reaction for the combustion of propane using a delta HF table and Hess's law, right? So in this case right here, let me just rewrite out the equation again, right? So we have C3H8 gas plus 5O2 gas yields 3 CO2 gas plus 4 H2O gas. Right, so we have all of these guys right here. So now we can just simply look on the back of the table of what we have. So for C3H8, right, if I look here again, right, we have -104, right? So delta H of formation of C3H8 in this case is -104 kilojoules per mole, right? The delta H of formation of O2 is 0, right? And 0, right, because O2 is the standard state of oxygen. So I already know that off the top of my head. The delta H of formation of CO2 is -393.5 kilojoules per mole. And then the delta H of formation, I'm just going to throw it up here, of H2O gas is negative 242 kilojoules per mole. Now, one important thing that can kind of trip people up with H2O, right, is that there's H2O liquid and then there's H2O gas, and both of those have different delta H of formations. So you want to make sure that you're using the right one for the state that you're in, right? So in this case right here, right, I'm saying that we're forming H2O gas. So you have to keep that consideration in mind. Right, it's not H2O liquid, and so right, those will give you two different values if you don't do that right. Right, so we have all these delta H of formation. So if we're looking at what the delta H of the reaction is in this case, right, that's just simply going to be, right, the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants, right? So now we can just, plug in everything that we have. And so delta H of reaction is going to be equal to, right, CO2. So that's 3 times the CO2 one. So that's negative 393.5 kilojoules per mole plus 4 times negative 242 kilojoules per mole, right? So that's all of our products minus our reactants, right? So 0, I'm going to completely disregard that, and there's no coefficient before the C3H8, right? So that's just simply going to be negative 104 kilojoules per mole, right? And so what we get now is 3 times negative 393.5 plus 4 times negative 242 minus negative 104. That comes out to negative 2,045 kilojoules per mole. Well, I wouldn't do per mole, right? Because you don't need to worry about that, because since you're multiplying by the number of moles in each case, that cancels out. And so that should match what I have on the key. Yeah, negative 2045. Yep, right, and that's how you get it, right? Negative 24 kilojoules, right? And so because, right, this is 3 moles, right? This is 4 moles, and this is 1 mole, right? All of those moles cancel out in these cases, right? And so you get a delta H reaction of that. And so that's one important thing to think about, right, with delta H reactions, is that they shouldn't, unless they're like normalized to one of the reactants or products, right? They shouldn't be per mole, right? They should always just simply be the energy unit. Because, right, that delta H value that you have for that reaction is completely dependent upon how many moles of each one of those reactants and products you're actually using in those cases. And so the appropriate thing to do, right, is not to have that be per mole, right? Because then the question is like, per mole of what, right? Because there's 4 different molecules, right? So it's per mole of what, right? So, I mean, we could easily standardize and say it's like per mole of C3H8. But you wouldn't want to just simply have it be per mole and not give any kind of qualifier, in my opinion. But yeah, so that's it, right? So those are the ones that everybody voted on, primarily, I think, because of the mistakes that I had in the key. But that's just how it goes sometimes. So I'm going to upload the corrected key in a second, and I'll post all of these things, and then hopefully that'll clarify any kind of questions that people have and stuff like that. So yeah, hopefully you guys have a good weekend. I'll see you guys Monday when we start, going over entropy and Gibbs free energy and adiabatic and isothermal compression and expansion and stuff like that. And it's going to be a lot more questions that you guys will probably have for that. So, all right, well, have a good weekend. Bye.